Have you ever asked yourself why some materials are radioactive? Why certain rocks or elements emit invisible energy, even when they seem to be just sitting there? In this video, we'll explore what makes some materials radioactive, how radiation is released, and why it's a natural and essential part of our universe. By the end, you'll understand how atomic instability leads to one of the most fascinating processes in science, radioactivity. Radioactivity is the spontaneous emission of energy or particles from an unstable atomic nucleus. It happens when an atom's nucleus is trying to reach a more stable state. This energy is released in the form of alpha particles, beta particles, or gamma rays. While the process is invisible, it can be measured, and its effects can be seen in both nature and technology. Atoms are made up of a nucleus containing protons and neutrons, surrounded by electrons. Protons have a positive charge, neutrons are neutral, and electrons are negatively charged. The number of protons defines the element. But it's the ratio of protons to neutrons that determines if the atom is stable or radioactive. In stable atoms, the forces within the nucleus are balanced. But when there are too many or too few neutrons compared to protons, the nucleus becomes unstable. To reach a stable configuration, the atom undergoes radioactive decay, releasing particles or energy to fix the imbalance. The chart of nuclear stability, also called the neutron-to-proton ratio chart, plots the number of neutrons versus protons for all known isotopes. Stable nuclei fall along a curved line called the line of stability. For light elements, stability occurs when n approximately equals Z. For heavier elements, more neutrons than protons are needed to offset repulsive proton-proton forces, so the line curves upward, n greater than Z. Isotopes far from this line are radioactive and tend to decay toward stability. This chart helps predict whether an isotope is stable or radioactive based on its neutron-to-proton ratio. There are three main types of radioactive decay. Alpha decay emits 2 protons and 2 neutrons. Beta decay, a neutron becomes a proton, or vice versa, emitting an electron or positron. Gamma decay, the nucleus releases excess energy as gamma rays. Each type has different energy levels and penetration abilities. Some elements are naturally radioactive. Uranium, thorium, radon, and potassium-40 are common examples. These elements have unstable isotopes that decay over time. They've existed since the formation of the Earth and are still decaying today, very slowly in most cases. Radioactive materials are found in soil, rocks, air, water, and even in living organisms. For example, bananas contain potassium-40, a naturally occurring radioactive isotope. Some building materials also contain small amounts of uranium or thorium. Isotopes are atoms of the same element with different numbers of neutrons. Some isotopes are stable, while others are radioactive. For instance, carbon-12 is stable, but carbon-14 is radioactive and used in radiocarbon dating. The difference lies in their nuclear stability. Radioactive decay is predictable over time. The half-life is the time it takes for half the atoms in a sample to decay. Some isotopes have half-lives of milliseconds, others millions of years. Understanding half-lives helps us date rocks, artifacts, and even the age of the Earth. Some materials have extremely long half-lives, meaning they decay very slowly. Uranium-238, for example, has a half-life of over 4 billion years. That's why we still find radioactive elements in nature. They haven't finished decaying since the Earth was formed. Not all radioactive materials are natural. Humans have created artificial radioactive isotopes in nuclear reactors and particle accelerators. These are used in medicine, industry, and scientific research. For example, technetium-99m is widely used in medical imaging. In healthcare, radioactivity is used for both diagnosis and treatment. Radioisotopes can help doctors scan organs, detect cancer, or destroy tumor cells. Nuclear medicine has improved the early detection and treatment of many serious conditions through safe, controlled use of radioactive materials. In industry, radioactive sources are used for quality control, material inspection, and energy generation. They help measure material thickness, detect leaks, and sterilize equipment. Nuclear power plants also use radioactive fuel to produce electricity by harnessing controlled fission reactions. You are exposed to radiation every day, from cosmic rays, the ground beneath you, the food you eat, and even your own body. This is known as background radiation, and it's usually at safe levels. It's a normal and unavoidable part of life on Earth. Radiation becomes dangerous only when exposure is too high or uncontrolled. Proper shielding, limited exposure time, and safe handling practices allow us to use radioactive materials safely in medicine, science, and industry. The key is understanding dose and duration. Radioactivity isn't limited to Earth. Stars, including our Sun, emit radiation. Some of the heaviest radioactive elements were formed in supernova explosions billions of years ago. Cosmic rays, black holes, and neutron stars are also sources of high-energy radiation in space. Since we can't see or feel radiation, we rely on instruments like Geiger counters, scintillation detectors, and dosimeters to measure it. These tools detect particles or energy released by radioactive materials and help ensure safety in labs, hospitals, and nuclear plants. Marie Curie, Henry Becquerel, and Ernest Rutherford were pioneers in discovering radioactivity. Their work laid the foundation for nuclear science and medicine. Marie Curie's discovery of radium and polonium advanced our understanding of atomic behavior and earned her two Nobel Prizes. Radioactivity is a powerful force. It can harm, but also heal. Like fire or electricity, it must be respected and managed properly. When used wisely, it brings enormous benefits, extending human life, advancing technology, and helping us explore the universe. So why are some materials radioactive? The answer is, because their atoms are unstable and naturally seek balance by releasing energy. This process, while invisible, has shaped the Earth, fuels technology, and saves lives. Radioactivity is not just a hazard, it's also a gift of science and nature.